So, we will start now the multi objective optimization problems. Multi objective optimization. So, if you recollect that so far we have discussed the solution of a single objective function by using what is called different techniques with equality constant and inequality constant. However, in real practice many designers are willing to optimize more than two or more than two optimization problems. So, that problem is called multi objective optimization problems or multi criteria optimization problems, or sometimes it is called vector optimization problems. So, if you want to minimize a objective function more than two or more than two with equality constant and inequality constant, then we will call it is a multi objective optimization problems. So, basic definition of this problem like this. Problem definition: in general, the objective function, a multi objective function, optimization problem can be represented as minimize f of x. F of x is a vector of dimension k into 1, which we have a n k objective function f 1 of x, f 2 of x and dot dot f k of x, and each is a function of x design variable and x is a n dimensional design variables, or one can write it in other words minimize f 1 of x, f 2 of x dot dot f k of x. We have k objective function, we have to minimize subject to the constant. Our constant are equality constant and inequality constants are there, subject to h I of x is equal to 0, I is equal to 1 2 dot dot p equality constant. That inequality constant may be linear, nonlinear, and our objective function also can be linear, nonlinear. So, our inequality constant x g j of x is less than equal to 0 for j is equal to 1 2 dot dot m, where our k is the number of objective function involved in the optimization problem. K is the number of objective function to be optimized. So, from this two inequality that m p equality constant and m equality constant, we will get the feasible region or feasible space. So, feasible set or space is defined, set or space is defined as x is the feasible region or set, where I will get it from x I is equal to 0, I is equal to 1 2 dot dot p and g j of x less than equal to 0 j is equal to 1 2 dot dot m. So, these are S is the feasible set. So, in general a multi objective optimization problem, we cannot get a single solution which will simultaneously minimize both the functions. Agree? In multi objective optimization problem, we cannot get a single optimal solution, agree, a single optimal solution that could optimize the both the objective function simultaneously. So, because of this, the multi objective optimization is not to search the optimal solution, but to find out an efficient solution which will make the both the objective function value is minimum as possible. So, multi objective, you can say note multi objective optimization is not to search for optimal solution, but for efficient solution that can be best attained, or that can provides the best solution, or that can provide best solution. Since we know in multi objective optimization problem, we cannot get a single solution that will simultaneously optimize the both the objective function. If it is two objective function, it cannot simultaneously optimize that two objective function. If it is more than two, let us call n objective function, k objective function is there, a single point solution, it cannot optimize all the objective function simultaneously. That is why we are looking for a multi objective optimization problem is not a search for optimal solution, but efficient solution can be obtained. Efficient solution can be obtained, can be attained. Efficient best solution can be attained. So, let us see with an example what we made this statement. So, so let us call, we will take in one example. Start with a simple example, two objective function minimize f1 of x is equal to x1 minus alpha 1 whole square plus x2 minus alpha 2 whole square. This is one objective function. Another objective function f2 of x, I am writing x1 minus beta 1 square plus x2 minus beta 2 whole square. If you look, both the objective function in its quadratic form, okay, and our subject to the constraint, let us call, we have just considered only for inequality constraints, that g 1 of x is equal to a 1 1 x 1 plus a 1 2 x 2 plus c 1 is less than equal to 0, and g 2 of x is equal to a 2 1 x 1 plus a 2 2 x 2 plus c 2 is less than 0. Look, these two objective function, these objective functions are nonlinear in more specifically it is in quadratic form, whereas our constants are in linear equation form. Agree? Now, if you plot these things in a graphically, look what we will see this one. Suppose this is the x axis, x 1 axis, this is the y 1 axis, sorry x 2 axis. These are the two equation, linear equation. Let us call g 1 of x I denoted by that one. Agree? This was our g 1 of x and its the inequality condition satisfy in this region, that above this line or on the line, let us say. So, this one is you can say g 1 of x is equal to 0 or it is g 1 is less than 0 in this side. On the line it is g 1 is equal to 0 and we have another line g 2 is, let us call it is something like this, say, and this feasible region is either on the line, either any point on the line when it is equal to sign is there, and if it is a less than 0 it is, let us call in this side g 2 x is less than 0 in this one, or on the line this is g 2 of x is equal to 0. So, if you see carefully, the feasible region of this optimization problem for multi objective optimization problem is our this region, feasible region. Or S feasible set is S this one. Now, let us see what is this our 2 objective function. Then one objective function, the center is here, let us call this center is here, whose alpha 1 and alpha 2, this one. Another is, let us call here, this is call is this center is beta 1 and beta 2. Okay. Now, you see this objective function f 2, this is corresponding to the f 2 objective function. This objective function value will be minimum when you draw a circle which touches this line g 2 of x, which touches the circle g 2 of x. If you draw a circle which will touches this circle g 2 of x. That means, the perpendicular distance from here to here, it should be perpendicular distance is the, let us call this is P 2. Agree? This is P 2. So, P 2 one can easily find out from the equation of this G 2 expression. So, our if you see this one, I will redraw this circuit, redraw this figure, because I have to make more conclusion from this curve. So, I will just redraw this one once again to make it more clear. I just redraw this one once again. So, let us call G 1 just showing, and this is our G 2, G 2 of x, this is G 1 of x, and our feasible region is that we have assumed this feasible region is that one. For feasible region of this one is above this line. Okay. just we have a point here, the circle of this one is beta 1 and beta 2, center of this one, and we have another is here, you can say alpha 1 and alpha 2. Now, if you look at this one, this is our feasible region. And feasible set. If you draw a circle which touches this line G 2 x, then it is that one, and let us call this distance from here to here is P 2. Okay. P 2 we can easily find out, and that is the, if you see the P 2 is the minimum value of the function f 2. This is the minimum value of the function f 2, that one, and it, this point is B, let us call. And what is the minimum value of the function from the center of this objective function is that one. Agree? Let us call this point is something else, let us call it is a this, but when this is the minimum, no doubt this function value is minimum, but that point which is lying on the G 1 axis, it satisfy the first inequality condition, but it does not satisfy the second inequality conditions G 2. So, this cannot be a optimal solution of this one. Agree? So, on the other hand, if you see this one point B for function f 2, for function f 2 is the optimum value of the function, and it is a feasible point, because B 2 lies, B 2 satisfy the what is called G 2 condition as well as the G 1 inequality conditions. B 2 satisfy the equality condition of G 2 and the inequality condition of G 1. So, this is the feasible point, but that is not the feasible point. So, what we can do it here, that we draw a circle of a radius this one. If you draw a circle like this way of radius, let us call this point is A. This is a circle. So, this, if you draw a circle with this one, then this point A is the minimum value of the function f 1, and which is a lies in the feasible region, because it satisfies both equality condition of G 1 and G 2. Similarly, that this one I told you it satisfy the point B satisfy the equality condition of G 2 by inequality condition of G 1. Now, the objective function of this f 2 is minimum, no doubt, but objective function of that one is, we cannot say the minimize both are that at this point is simultaneously it minimizes that one. Okay. So, we can point out now the point A is the minimum value for f 1 function, f 1 objective function. If you just draw another circle which radius is greater than this one, then this is a feasible in this region, but that is not the minimum value of the functions. Whereas this value is the minimum point, but they are not coinciding with the same point. So, therefore, next is I can tell you this one, the point B individually, if you think point B is the minimum point value for f 2 objective function. Agree? Now, because this at this point this is the minimum value of the function, whereas the function f 2 has a minimum value of the function is b 2, but at a single point both the function are not simultaneously minimized. Okay? So, we cannot expect that there is a single point for which both the function will be both the objective function will be simultaneously optimized. So, we are looking for not for a we are not searching for a optimal solution for a single point optimal solution, we are looking for best efficient solution that will satisfy that will give you the best optimal solution. So, let us see so we can make a conclusion now, but which look at this point as I mentioned here, this point is minimum for this f 1, but this point is minimum for this point of this one. Now, which point will give you the simultaneously both the function, if you just add it will give you the minimum value of function. So, we have a so many points are there, from there we have to pick up which one is the minimum of objective function value, minimum sum of the two objective functions. So, but which design that minimizes both f 1 and f 2 simultaneously. But this is not clear even for a simple two objective functions. You see two objective function we have considered, but it is not clear which at which point we will get the f 1 and f 2 simultaneously minimum. Simultaneously minimum minimization this one. So, therefore, what we are looking for? Therefore, if one wishes to minimize f 1 and f 2 simultaneously, then pinpointing a point is not possible. Then particular point or pinpointing a single point is single optimum point, you can write single optimum point is not possible. So, you have to do some compromise. So, in fact, there are infinite many possible possible solution points called Pareto, the Pareto. Look at this point. Suppose I am telling you at this point a point this function is f 1 function is minimum, but it satisfy the all constraints. At this point this function is minimum. So, if you increase this one, this function is increasing, function value is increasing, agree, but this function if you make it same, but this function is value. So, function value is now increasing. So, you have to find out some point which directly not minimizing the both the function simultaneously, but some of the two function value will be minimum. So, now now let us see this one, what is called, we plot it here, criteria space. That is f1 of x in this direction, then f2 of x in these directions 0. The criteria of this figure represent the graphical representation of two objective function in criteria space. The graphical representation of two objective function, because we have taken the example of two objective function functions in criterion space, and criterion space is denoted by Z. What is mean by criterion space? That we have a two inequality constant will move along this line G1 and also G2, and we will plot the value of function corresponding to G1. If you move along the G1, and we can easily find out what is the function value of f1 and f2. Let us call at this point, we know x1 is what, x2 is what. So, we can find out the value of f1 and f2, plot it, f1 versus f2. Then next another point you take it, you know x1, x2, find out the value of f1 of x, f2 of x, plot it in that space. So, that space what will get it, f1 versus f2, that is called criteria space. So, if you plot it this one, let us call we are getting this curve. Agree? Another curve, this is for, let us call it is a Q2. So, Q2 represents the G2 boundary, G2 of x boundary. What does it mean? This is the G2 of x. So, any point on this one, let us call, if you take this point, I know x1, x2, then correspondingly f1 and f2 you plot it, and along this line when G1 is 0, along this line you plot, if you plot it, that is Q2. Similarly, if you move along the G1 axis, G1 straight line on the line, you will get Q1. Q1 represents the boundary of G1. So, let us call Q1 is like this way. So, this is Q1, that is represents the boundary, represents the boundary of, represents the G1 of x boundary. So, this is the boundary of this one. So, inside this G1 is this region, and inside the G2 is this region. So, what is the common space of that one? If you see, so our criteria space is that one only. So, that is the criteria space. Now, look at this point, that is what I am telling it here. If I make a circle here, if I make a circle here with a radius b, Agree? This function value f1 function value, this I will call, this is the function value of f1 at b, and this function is f1 at a. So, this function value will be what? This is the common point for both the, this is a common point for both the objective function of this. You can say this is the our optimum, this is the our one of the solution, but whether solution is the Pareto optimal or not, we do not know. And one another thing, we can draw it here by centering this one with this point of this one. So, this is the f 2 of a, and this point is f 1 of b point. So, now you may say that this point, whether it is a sum of the two objective function value is less than the sum of the objective function of. So, what we can say, the f 1 a, sorry, we can write it now based on this one, that f 1 a and f 2 a, this point, sum of this function objective function, whether it is less than the f 1 b plus f 2 b. This is f 1 b is, this is the f 2 b, sorry, this is the f 2 b, and this is the f 2 b, this is f 1 b. Which one is less this? We do not know, but we have to search for this one, for which we will get the, there are infinite number of points, okay, that for which the function value, you see this function value is increased, okay, but this function value is decreased. Whereas, if you see in this case at this point, the function value of what is called f 1 a is minimum, whereas the f 2 b, f 2 a value, f 2 a value is, f 2 value a is increased. So, we do not have a clear cut answer at what point, whether a point, b point or other point, we will get sum of the two objective function is minimum. So, if we take in another point, let us call this point is that point, if you can take it, we draw a circle of this one, this point, okay, which crosses this one, and that is, if you see this circle, if you draw a circle over there, our feasible region is from here to here. And this portion is infeasible region, this feasible in infeasible region. So, let us call this circle, I am considering this one now. So, we have a, so now let us see this one. If you want to represent this thing in here, so let us call our D point is here, our, let us call our B point is here, A point is here. We draw a circle which is passing through this one, another point is that one, it cuts here, let us call this is the cuts is, here is D point is here, which cuts that circle, which passes to the A point of f 1 of A, D point. Then we have a, it cuts that point here, that is our, we can say this point is our C point, agree, this is the C point, and this is the another point which cuts is here, let us call this point is, this cuts here, here, that is the E, let us call this is F point. Now, see this one, and I told, as I mentioned it here, that this region is the our feasible region. This region is our feasible region, and this is, this point E point and F point is satisfy the G 1, it satisfies the G 1 condition, but it does not satisfy the F 1, F does not satisfy the G 2 condition, whereas E satisfies the G 2 conditions. Agree? And if you see the D point and as well as the C point, D point satisfy the what is called G 1 condition, but C point does not satisfy the G 2 conditions. So, in this way we will see that there are some points are there which will give you the sum of the two objective function value is minimum. Okay. So, if you plotted this one, from there we can find out the region where is the our what is called criteria space. This is the criteria space of that one, and this is we got it from the design space by finding out the objective function value along the constraint that G 1, along the constraint G 1 of x 0 and G 2 of x 0. This is corresponding to G 2 of x 0 and this is corresponding to G 1 of x 0. So, you will just give some definition of that one now, some of the important definition of that in context to the what is called multi objective optimization problems. In general, a curve in the design space in the form of G j x is equal to 0 is translated into a curve Q j in the criteria space simply by evaluating the value, simply by computing the values of the objective functions. At different points along the G 1 on the surface of G 1 or G 2 functions at different points on the constraint curve, on the constraint curve in the design space. That is what we have done it, this Q 1, Q 2. So, there are some of the terminology generally used in objective what is called multi objective optimization problems, that is called solution concept. So, first is Pareto optimality. What is this? Suppose a point x star is a point x star in the feasible or design space, in the feasible region or in the design space. x is the in the feasible or design space, S is the Pareto optimal if and only if necessary and sufficient condition, if and only if there exist there if and only if there does not exist another point on the in the feasible region, another point x in the set S is the feasible design space such that f of x is less than equal to f star of x. This there is no such x is there other than x star that which function value will be less than this. We have a how many functions are there? K functions are there. Any function of that f 1 f 2 should not be less than this. If it is less than this, should not be less than this one. Agree? With at least one f 1 of x is less than equal to f 1, rather let us call it in the other more general f I of x star I is equal to 1 2 dot dot k. In any one of this is violates this one, it should not be less than this one without increasing another one. So, a point x star is said to be optimal, what is called Pareto optimal, if there does not exist any feasible point inside a feasible region such that this condition does not satisfy, this condition does not satisfy, agree, without increasing any other function values, then we will call it is a parity optimal solution. Agree? Parity optimal solution. Another this one is weak Pareto optimality. This definition is exactly same as this one, only inequality sign, only it is a strictly inequality sign will be replaced. So, a point x star in the feasible space, in the feasible design space, the feasible design space S is weakly Pareto optimal if only if and only if necessary sufficient there does not exist any x, another point that does not exist another point x in the design space S such that f of x is less than equal to f star of x. That is, there is no point, in other words, what does it mean? There is no point exist in the design space for which the objective function value improves means less than that one. This implies that there is no point no point that improves. Improves means the value of the function value is reduced further, that improves all the objective function simultaneously. The difference between this one is here that if you further if you say further decrease of the one, but in the other case is without increasing the another one. It may be same, but not increasing this one. But here it does not improve all the function values simultaneously. This is the weakly Pareto optimal, and basically there are two more definitions are there, which are called efficiency and dominance. Efficiency is the another primary concept in multi-objective optimization problems. This is the another, you can say, another primary concept in multi-objective optimization problems. So, let us call what is this efficiency indicates this one definition, a point. This basically efficiency and Pareto optimal definitions are exactly same. A point x star is the in the feasible design space S is efficient if and only if there does not exist another point x in the set S such that f of x is less than f star of x with at least f I of x, f I star of x that does not exist with at least, otherwise x star is inefficient. So, this next is dominance. So, I just mentioned is that there are two concepts is generally used in efficient and dominance. So, another common concept is the non-dominance and dominant points in a multi-objective optimization problems. So, non-dominated and dominated points. So, these are defined in based on the what is called criteria space. A vector, because our objective function is a vector f 1 f 2 dot dot f n, a vector of the objective function f star of x in the feasible criteria space z star z, a vector objective function f star in the feasible criteria z is non-dominating netted. Mind it, when we are talking about the feasible criteria space, that means we are going along the that area. If you see this one, this is the criteria space, this boundary is indicates the along the G 2 constraint and this boundary constraint the G 1 constraints, and along this side is the criteria less than this indicates the value of the function, value of the objective function inside this region indicates the value of the objective function which is on a inside the feasible region. So, is dominated non-dominated if and only if there does not exist another vector, another f f in the solution set, in the set Z, means criteria space. Such that f of x is less than or equal to f star of x, but it is in the criteria space with at least one f I of x is less than f I of x star, otherwise it is dominant, otherwise f star is dominant. And last point associated with the multi-objective contest with library, this utopia point. Now, you see this one utopia point is, if you look at this expression. Now, let us call this one, agree. If you see this function f 1, when it is passing through this a 1, the function value is minimum. When it is function f 2, when it is passing through the point B, it is a optimal. But that 2 points are not the solution of this one, it is not the common point that solution of this one, and that point you can easily see it must be the outside the what is called criteria space. How? That see this one, this point is on the surface of the on the boundary of Q 2, and this is on the boundary of, if you see this one, this is on the boundary of what is called Q 1. One is on the boundary of Q 1, another is on the boundary of, this is on the boundary of Q 2 and this is on the boundary of Q 1. So, where is the utopia utopia point will be, definition of this one, a point f 0 in the criteria space, Riemann space, is called the utopia point if f I we have a how many function objective and k functions are there, f I is minimum of f I x I, this for this indicates for all, I am talking about f I for all x in the design space. S for I is equal to 1 to k. So, if you see this curve utopia point of this one, let us call this is our Z 2 and this is our Q 1 and this is our Q 2 point, this one, and our utopia point is outside the what is called our feasible region. This is the outside of our feasibility. This is in this direction f 1 of dot, this is a f 2 of dot. See this one, if you see this one, that is, and this point it is lies on the q 2 and this point lies on the what is called q 1 point. So, q 1 point and q 2 point. In other words, what we say this one, this is the minimum value of the function and this is the minimum value of the function. If you plot it here, you will be here minimum value of the function, and this is the utopia point of this one. By definition, it is nothing but a point in the criteria space is called utopia point when f I is minimum, f I is minimum for all x in the design space, because this is the minimum for all feasible region, this is the minimum point and this is the minimum point for all, but that point is outside the what is called our Z space, which is called criteria space. So, we will stop it here, and this is correspondingly this point, you can say this point f 1 of A and this is f 2 of B point, this utopia point. So, from next class we will start with a what is called the dynamic optimization problems. So far we have discussed last few lectures is a static optimization problem, starting from single variable case, nonlinear, how to solve the optimization problem using the what is numerical techniques, then linear programming, nonlinear programming, all these things we have discussed, and lastly we have given the some basic idea of multi objective optimization problems and related some definitions. We have seen that there is not possible at all to find a single optimum point, single point for which both the objective function or all the objective function, multiple objective function will be simultaneously minimized. So, there must be a what is called Pareto optimal point. So, here we will stop here.